Here we wanted to integrate 2x plus 5 times the square root of x squared plus 5x plus 10 with respect to x from 0 to 9. Let's go ahead and start attempting to do this. What you should do is you should treat this, since we know it's going to be substitution, as a normal substitution finding the antiderivative. So we want to find the antiderivative first. In order to do that, I have to do a u substitution. U is equal to x squared plus 5x plus 10. And the derivative of u with respect to x would be 2x plus 5. That's nice because my differential exchange, I can replace a 2x plus 5 multiplied times dx with a du. So I take my integration, and I like to rewrite this. I'm going to take the 2x plus 5 component, and I'm going to stick it back next to the dx, just for the sake of it looking nice. And then what I'm going to do is I'm going to replace that 2x plus 5 times dx. That can all get replaced with a du. And the square root of the polynomial is just the square root of u. Once I've done that, I should say, well, I'm not using x's anymore, so I don't want to say from 0 to 9 anymore. It's going to be from some other number to some other number. Don't really care what those numbers are. I just know they're not my x's. Square root of u, when I take the antiderivative, it's going to be easier to see that as u to the 1/2 power or u to the 0.5 power. That way, when I find an antiderivative, it's going to be 1 over 1.5 times u to the 1.5 power plus any constant that we want. Since we're doing a definite integral, I'm going to choose the constant of 0. And then my bounds, well, I'm going to write 0 to 9. That's actually incorrect. It's going to be from somewhere to somewhere, some u value to some other u value. But once I've done this, then I can start going back to an antiderivative with respect to x. Remember, my u in this case was x squared plus 5x plus 10. By the way, 1 divided by 1.5 is 2/3. So I like writing that as 2/3 better than this. Because we go back to x, we can go back to using bounds of 0 and 9. At this point, we plug in our 9 and plug in our 0. Let's go ahead and do that. Sorry. Plug in 9 minus, plug in 0. So plug in 9 first. I would get 9 squared plus 5 times 9 plus 10 on the inside. If I plug in 0, I would get 0 squared plus 5 times 0 plus 10 on the inside. I'm going to type that into my calculator, this whole thing. When I computed that on my calculator, I ended up getting a 1036.26, or I should say approximately that number. It's not precisely. It's about 1036.26. It goes on for a little bit more decimals. So there you go. That's how we can use definite integrals along with substitution and the fundamental theorem of calculus. I should rephrase that. We can use substitution along with the fundamental theorem of calculus to solve these types of definite integrals. Now, the last thing I wanted to say is that we did a lot of integration and finding antiderivatives previously. Now we have another technique to find antiderivatives. That is substitution. But we have to realize that substitution is just one technique. And there's going to be a lot of integration, a lot of integrals that you can't solve using a direct substitution technique like the one we've been doing. We're going to look at another technique in the next section, but I just want to make that note. Direct substitution will not work for every integration problem. And here are two integration problems where direct substitution would not work, would not help you out. So we had our basic rules of integration. Now we have our substitution rule of integration. And we can see that those two techniques aren't the only two that we really need. So this is kind of what the chapter 6 is all about in the calculus book. We're not going to cover all of chapter 6 in calculus 1, but if you go on and do calculus 2, you'll find lots and lots and lots of other techniques and really interesting techniques that you can utilize to do integrals.